Hello and welcome to the first of the ELEC2540 virtual labs. I don't know how successful this is going to be, but we shall see. So all you're going to be able to see at the moment is my hands, I hope, if this is camera set up properly. And this is my snowboard on a piano stand in order to show you my bits and pieces for this experiment, okay? So the first thing we're going to look at is the magnetometer, which gives us actual cardinal positions, i.e. 0 through to 360 degrees or 359.9 degrees. So here we have the main compass drive unit, and this component here is the magnetometer, which I'm hoping you can see quite clearly here. This is a MEMS device, and it's actually a mixture of all sorts of bits. It's an accelerometer, a gyro, an inclinometer, and a magnetometer all in one package. And it works through I²C. So we're using that as our interface, which is what these wires are for. So these wires produce the deliver the power and the communications for I²C in order to extract the data from this device. So this connection goes through this assembly, and inside here is a slip ring. So this allows complete rotation of this device whilst also maintaining an electrical connection to this port here, which will be connecting to our compass control unit. So at the moment I'm not too sure where north is here, but let's just assume it's in this position. So the compass project as a whole is trying to maintain this position, and so as the compass pointer moves, we actually want this mechanism to pull it back to north to get it always in the north position. So that's our set point. It's a bit like an oven control system, where you might have a temperature that you set on your oven for, say, for example, 200 degrees centigrade. And what the oven is trying to do is maintain that 200 degrees set point. Well, what we're doing is we're saying our set point is north, and that by definition in the inclinometer is 0 degrees. And so we're trying to maintain 0 degrees from the inclinometer. So we're communicating with this device and actually getting the information. So if it was in this position, let's assume that is north, then we would get 0 degrees back. However, if it was in this position, we'd actually be getting approximately 180 degrees back. Now the data coming back from the inclinometer is actually in tenths of degrees. So we would be getting here 1800 degrees, so it's actually in tenths, and here we'd be getting 0. And in this position, if you can still see it here, we'd be getting 900, which equates to 90 degrees. And similarly, if I move this over here to that position, and that would be 2700, which would be 270 degrees. So in the software we correct for this, and we also change it so that when we're in the north position, when we're going around in the clockwise direction, we're going from 0 through to plus 180 degrees. But as soon as it crosses over that point, it actually goes to negative 179.9 degrees, and then it gradually goes here to actually minus 90 degrees, and then through to 0. And this allows the control system to be able to determine, so when it's in this worst case position of 180 degrees, it can actually choose to drive the system in of going from positive direction, so going from 180 through back to 0 that way, or from minus 179.9 and going negatively in this direction back to 0 again, if that makes any sense. Probably makes more sense when we actually do it for real. So what else is on here? So we obviously have to drive this compass unit, because at the moment it's just free rotating through its slip ring. Great stuff, eh? Right, okay, so what we're going to do is, so how do we drive this? Well, we drive it through a continuous servo. And continuous servos differ from standard servos. In the standard servos, what happens is when you give it they all work in the same way in terms of pulse requirement. So we've got a pulse width of a period of 20 milliseconds, which is standard for PWM servo drives. And it's got a 7.5% duty cycle, which my MEC 2200 students will know all about. But if you don't know anything about this, then it's PWM for servos, for these types of servos, is 7.5% duty cycle. And that means that there is a pulse period, a pulse width of 1.5 milliseconds within a period of 20 milliseconds. And the 1.5 millisecond period pulse width actually defines the center position. So if a servo, normal servo, standard servo was there, then let's assume our servo is giving a pulse of, or given a pulse of 1.5 milliseconds. Then if we actually increase that pulse width, so we actually go, and it's only allowed to travel between plus 500 microseconds and minus 500 microseconds. So if we go towards 1.5 milliseconds plus 500 microseconds, and what will happen is the standard servo will start to move in this direction. And then once you give it a full 500 microsecond additional width, then it will lock itself in that position. And as that value decreases, then it will change like that. Similarly, if we actually take that 500 microseconds pulse and we actually subtract it from the center position of 1.5 milliseconds, it'll actually go in the opposite direction. So it'll then fix it at this point. If we go to, for example, 1 millisecond, which is the maximum variation we can make in that negative direction. So that's a positional signal that standard servos get. But continuous servos don't work that way. Now, continuous servos actually, when you actually change the actual pulse width from its nominal 1.5 milliseconds, what will happen is it will actually start to continually rotate. So if I give it a small offset, say for example 30, 40 microseconds, it will very slowly rotate in one direction. If I now, so like, if I go higher than the 1.5 milliseconds, and I say, for example, add another 30 milliseconds to it, then it will go in the opposite direction. So by going positive from the nominal 1.5 milliseconds, it will go in one direction. And if I go negatively relative to this center position, it will start going the opposite direction. And the speed at which it does that is actually dependent on how much of an offset there is. So the larger the offset, so if I put in the maximum offset of actually 2 milliseconds, which is 500 microseconds plus a nominal 1.5 milliseconds, this will be going around as fast as it possibly can in this direction. Similarly, if I go my nominal 1.5 millisecond and actually take away 500 microseconds, then it will actually go in the opposite direction as fast as it possibly can. Now this is really important because we need to characterize the servo. If you want to understand control systems, you need to understand the drive capability of what's going on and what's the timing of these component parts. So here we have our servo, which is our continuous servo, and connected to it is a pulley mechanism. And the pulley actually then makes this connection rigid between the compass and the servo. And you'll notice, if you can see here, you'll see 3 different pulley positions. So if I just move that out of the way so you can actually see a little bit more clearly and try and point that, I hope this is going to work. You'll see that these 3 pulleys provide different drive linkages. So if I put the rubber band here in the center position, let's see if I can do it now. I'm going to put that in between there and there. Right. So like now, so this is on a 1-to-1 ratio. So it means that for 1 turn of the servo, I get 1 turn of the pointer, like so. And similarly, if we actually change this pulley ratio, just moving this out of the way, and we actually now put this onto the smaller pulley on the drive, and we put it onto the larger pulley on the arm, then let's just see what happens here. So now that for a rotation here, it slowed the whole system down. Now this is really important because it helps you to understand the relationship between these drives and actually what's the effect in terms of the algorithms that are used and the constants you use within your PI control system. So this is now much slower response time. And similarly, we can actually make it a much faster response time by putting it onto the lower setting. So just do this. Hope I don't break the band because I can't get into Uni to get along one. So now you'll notice that if I turn this, we get a much faster response. So it's a 2-to-1 ratio. So, sorry, it's a 1-to-2 ratio. For one turn of this, we get 2 rotations of the arm. So this is important to understand. So what we're going to do during the experiment is characterize this servo. For one, to find out whether it's linear, because we actually don't know what the response of this servo is. So we need to know that in order to help us understand control systems in general. You may argue, well, it's not important, we're just going to do the figures and, you know, we'll work it all out. But it is really important to understand what's physically going on here. If you're making a PI control system, then you need to understand the components that are in that system so that you know what the limits are, where your failings might be in terms of, well, if I use this algorithm, is it really the best algorithm to use, or can I adjust the software to make it better and all that kind of stuff. Now, this is not a software exercise for you guys. This is an analysis of PI control systems. But I'm asking you to think about this more carefully so that you actually broaden your knowledge of what's going on in these systems, okay? So I'm just going to put this back to a 1-to-1. If I can find it on there. There we go. So you have it back as a 1-to-1, and like so. For one rotation here, we get one rotation of the arm. Now then, so this is the compass control unit, the compass drive unit, and all of this is controlled through this 5-pin DIN socket here. So we're going to now move on to the control unit. So I'm going to put that to one side. And here we have the compass control unit. So you'll see on the side here, it's got power supplies. These are 2 split power supplies. It's internally connected. So all we're going to do is have 2 isolated power supplies, both at 12 volts. Negative, positive, negative, positive. I0 plus 12, 0 plus 12. And that's our power connection to this unit. This little switch on the side doesn't do anything. It's connected internally, but I haven't actually turned it into any functionality since it hasn't really been necessary to do that. Here's our connection to the outside world, which actually goes to our compass unit. So I'll bring our compass unit back. And here we have a 5-pin DIN connection, and if I stick this in here and put that into here, I can now talk from here to this. I can get the information from the magnetometer back into the processor, and also I can control the servo. So I can control the PWM to the servo, therefore I can control the speed of rotation of the servo. Just one other thing about servos, in particular continuous servos, is that they need to be nulled, so that there's a little, you can't see it in here unless I take this apart, but there's a little potentiometer inside here that generally when you switch it on and you power it with a 1.5 millisecond pulse with this, on the 7.5% duty cycle, then this servo, when you first power it up, will start to rotate. Now, what you do is you adjust the little screw inside, a little potentiometer, and you can get it so that at 1.5 milliseconds, this servo doesn't rotate at all. And so you just tweak it until you get that null point. So all of them are done like that, but I'm going to talk about something else about this when we talk about the software inside this unit. So this is our connectivity, and let's have a look at this more closely. I don't know how well you can see this, but we've got 2 power indicators on here that tell us that our power supply has actually been going in correctly. And also we've got some test points at this point. And let me just turn this around. I'm not too sure how clearly you can see this, but we've got a common 0 volts, that's for our oscilloscope, and we've got a trigger output here, and we've got 4 DAC, high resolution DAC outputs here. And so this is actually allowing us to look at the maths in real time on an oscilloscope. So channel number 4, which is, I haven't got my glasses on there, channel number 4 here actually in general will give you the what's actually the positional information from the from the compass. So it gives me absolute information back from here, so I can actually see this on the oscilloscope. So if I was to set this to rotate constantly, I would actually see a very distinct waveform coming out on this channel 4 pin. So channel 1, channel 2 and channel 3 are used to show different things within the algorithms. So when you're doing proportional control, channel 1 is actually giving you the absolute error between the north position, which is 0, and what's coming back from the inclinometer. So we said that this was our north position. So if I rotate this slightly, I will come back with, say, for example, 10 degrees. And so I will actually turn that number into an analog value and actually be able to see that for real. So I can see the actual error actually on the oscilloscope screen. So what's going to happen is I will see waveforms. As this attempts to continually try and find north within our algorithm, it will show me what's physically happening as an error signal, which is the most important part of the feedback system within any control system. We need to know what that error is in order to be able to get the system to reduce that error to nothing. That's the whole point of these systems, okay? So, and we'll discuss these test points in more detail when we actually look at the actual control algorithms and during the testing procedures, which we're going to look at later on. Now then, the final thing is, well, how do we control all of this? Well, all of this is controlled via an HMI. And here, you can put this to one side a minute. So here is a cable made by FTDI, a fantastic company, and they make USB to thing converters. So this one is a USB to RS232 TTL 5 volts, which means that I'm actually connecting this from my laptop, and it allows me to communicate into this socket here, and I can now, using a terminal emulator, just get that to stay still. In fact, just take that off a minute. So putting this comp cable in, putting this into my computer, and I can run a virtual terminal, which is MTTTY software that many students, especially MEC 2200 students and ELEC1406 students have used, because this is what I use for many of my labs, because I want you to be able to control things very precisely. And it's a great way of doing this. So I'm not using any high-end software on Windows or whatever it is. I'm actually going to create the HMI from the processor that's inside here. The processor inside here is a microcontroller from the PIC family microchip, and it's a PIC 16F1779. And the reason I chose that is because it happens to have 4 high-precision DAC outputs, which is what these are. There's also a general-purpose processor, and I use it in a few other labs that MEC 2200 students will be very aware of. So by running, putting this into my computer and then running the terminal software, then when I switch all of this on, then this processor here is actually sending information to the screen. It's called an HMI, Human Machine Interface. And so it allows the user to then select options to actually control this whole unit, which we're going to look at in detail shortly. Now, one of the really important things to understand about the setting up of this is that microchip processors can be powered in several ways. They don't necessarily need power on their VDD pin. And in fact, it actually, interesting, I only discovered it when I was messing around with this and I designed it, was it also takes its power from communications. So if I connect this into my laptop, which is powering this device and also powering the communications, when I plug this into here, it attempts to power this board. But as you probably realize, with all of this connected, let's put this in here, and I put all of this on, there is no way that this comms is actually designed to power all of this. And so what happens is you get a very, you get a small amount of voltage in there, probably about 2.5 volts, and because it hasn't got the current to be able to supply the whole thing. And what happens is the system doesn't initialize properly. And for this reason, it's really important that when we put this cable in, we actually power this all up first and we initialize everything. And then when we've got everything powered up and everything's working, I can then plug this into my unit. And when I've done that, then I can talk to it. But if I put this in and then switch the power on, then this will not initialize correctly. In particular, the bit that won't initialize properly is in fact the inclinometer, the MEMS device, which really does require a particular type of power up in order for it to work correctly. So sometimes if you get this wrong, you might see letters coming up on the screen which are indicating failures of the I2C interface. And if that happens, then I know I haven't powered it up properly, or it just needs power recycling, which may or may not happen as we go through these videos. So I hope that explains roughly what's going on here. And as I said, all we're trying to do here is get this system with an algorithm that we're going to put into here. We're trying to get this so that this stays in the north position. Regardless of how I turn the box, this compass pointer will always stay in the north. And what we're also interested in seeing, well, what is actually happening? If I put it into its south position, then how well does it respond to when I switch it on and tell it to go? How quickly does it get back to the north position? And does it do an overshoot and then come back? Or does it sit there and oscillate like this? And these are things that the whole point of these experiments is actually going to look at, investigate, and will actually hopefully give you a great deal of knowledge about how PI or P control systems and PI control systems work, and the importance of understanding the nature and the transfer characteristics of these components, because without that you're just guessing and it just becomes a black art. But with knowledge and understanding, you can turn this into a really valuable exercise from which you can carry that through to your career and hopefully understand PI and PID, although we're not doing differential control systems, but understand the principles behind all of this, but with a deeper sense of knowledge. Okay, and I'm going to try and switch the camera off now so we can move on.